During a steady-state operation, a gearbox receives 60 kilowatts through the input shaft and delivers power through the output shaft. For the gearbox as the system, the rate of energy transfer by convection. So means since the gearbox will be heating up, it will release heat to the surrounding at this rate, negative HA TB minus TF. Okay, where H is equal to 0.171 kilowatts per m squared Kelvin, and the heat transfer area is 1.0 m squared. And the temperature of the gearbox is maintained at 27. The temperature of the surrounding is at 20. That's why the gearbox will be releasing heat to the surrounding. Um, for the gearbox, evaluate the heat transfer rate, how much is the heat transfer rate, and how much is power delivered through the output shaft. So since we're familiar with the gearbox, let me show you how the gearbox looks like. Okay, so here's a sketch of the gearbox. The purpose of the gearbox really is to, normally in this case, to increase the speed. I think it will, right? To increase the rotational speed. Like this is the input shaft where you add here 60 kilowatts. In this case, work is being what? Done to your system. Your system is assumed to be your gearbox. In this case, work will be positive, right? Positive yung work is added. Now, the gearbox will do work to this shaft, meaning the gearbox will do work, meaning work will be uh, sent to this shaft, which is connected to the surrounding. This one you input work, this one you output work, and it's not only that because your gearbox is at 300, the system is at 300, and the surroundings only at 293 or 20 degrees Celsius. There will be what also heat transfer, where heat will of course will be leaving through your gearbox system. So in this case, we're being asked for that. How much is that, and how much is this work? Like let's label this as work to work down by the system towards the surrounding or the output shaft. Now, you can always remember that we'll have this formula. This is a closed system. No mass enter and no mass leave. So you could use this principle. Delta U is equal to Q plus W. But this is not on a time basis. This is essentially um, uh, the total change in internal energy will just equal to the Q heat added to it and the work done to your system. But if we take a look at this on a what they call that on a flowing base like Q, like we'll have this differentiate this with respect to time. We'll have delta U dt. Okay, delta U delta t Q delta t delta Q delta t, and we have here delta U delta t. In this case, this will then become what? Q dot, meaning how much heat is added or removed to your by your from your system, and work will over the change in time will just be W dot, meaning rate work per unit time, and this one du dt. And what do we mean by that? Meaning like we can have here like du dt. how how fast is the internal energy is changing with respect to time. In this case, we are assuming here that we are only reaching a steady state, meaning things are going steady. Temperature of your system is fixed already at 300 Kelvin, and the temperature of surrounding also is 293. And that in that case, when things are going steady, this internal energy is a property of the system will no longer be changing because that is already the energy, meaning it will not be changing. The gearbox will keep on operating, but its internal energy will not be changing anymore because things are going steady or we already have reached steady state. So this will then become simply zero. Steady state, the internal energy is no longer changing. In that case, it will become zero and we'll then be getting Q dot plus W dot. Okay? And note here that no, there's no boundary work, there's no expansion work. The work that we have is only work done by the shaft. So in that case, we're looking for Q, right? We're looking for Q. So therefore, um, okay, to solve for Q, how much heat is being released, we can just simply use what the equation. of this equation. Okay, by heat transfer, let's put values to that. Q will then be equal to negative H, where H is equal to 0.171 kilowatts per m squared Kelvin multiplied by area. Area here is 1.0 meters squared. That's the surface area of your gearbox, the covering perhaps of your gearbox, and then we have here TB minus temperature of the gearbox minus that of the surrounding. Gearbox is at, I'm using the 20, no, gearbox is at 27 degrees Celsius and the surrounding is at 20. Or you can use also the Kelvin, it doesn't really matter, 20 degrees Celsius. Okay, and this Kelvin and Celsius essentially are just the same in terms of delta T, so they simply cancel, and the meter squared cancel. So what will be left here? It's not really Q, but more or less it's Q dot. Okay, since it's already kilowatts. So in this case, we'll be getting negative 1.197 kilowatts, meaning heat is being released to the surrounding at this rate. And every second, there's 1.197 kilojoules of heat being released. And from there, we can actually compute now for how much is W2. Okay? In this case, we'll have 0 is equal to Q dot. It's negative being released to the surrounding. 1.197. Okay, negative 1.197 kilowatts, and then W will be, there are two W here, one W being added and W2 being removed. Okay, in that case, well, we have here added, it's 60 kilowatts, so we'll have plus 60. Then since W here is work is being done by the system to the surrounding, let me put the negative for that, minus W2, and therefore W2 based on that will then be equal to approximately 58.8 kilowatts. So note that the positive here doesn't mean that the work is being done um to the system, but since I put already the negative in there, but if I just be consistent with my unit, like I put a positive in there, I'll be getting here a negative W2, meaning, oh, well, work is being done by the system to the surrounding. Okay, so I think that will be a better idea. 60 plus W. I add all the W and here the Q. So this implies that the gearbox actually loses part of its energy. So meaning, supposed to be a perfect gearbox will be if you input 60 kilowatts of power here, the output that you'll get supposed to be is also 60. But as you can see in here, you input 60, you only get 58.8. Part of it is lost due to the friction inside, and that's the idea that is being manifested by the increase of the temperature of your gearbox. The surrounding is only 20, but your gearbox is actually at steady state, it's already at 27. That's why you are also losing, mostly because of friction. That's it.